In this lesson, we're going to learn a little bit about current electricity. By the end of the lesson, you should know what a series circuit is, what a parallel circuit is, and how to solve for the voltage, resistance, and current through any of these circuits. So in order to draw circuits, we have to draw a few symbols. We have to know what they are. We will not be using all of these for our level of physics, but there are some important ones. First one on the list is a conductor. This is what we typically think of as wires, but really it can be any conductor. Just a straight line connecting 2 points. Second one is a switch. The purpose of a switch is to interrupt the flow of electrons. So you'll notice that this switch here is in the open position so that electrons cannot flow through the circuit. We won't talk about fuses or capacitors in this lesson, but we will talk about resistors. Resistors are drawn with a sawtooth pattern connecting in line with some conductors. And this is any general resistor. We will see different examples of things that reduce the potential, but that is the general and most general type of resistor that we will see. We will not look at potentiometers. We will look at lamps. You might see some of these. This is a specific type of resistor. Now, if you've taken mechatronics, resistors are very specific things that you can put into circuits, but for our purposes, anything that reduces the potential we can draw as a resistor. A lamp is just a specific type of that. Going along the bottom side here, we will look also at voltmeters, which measure the voltage across a resistor or 2 different points in a circuit, and an ammeter, which measures the amps, the amperage, or which is the current through any part of the circuit. We'll look at those in a little bit more detail later. For an electrical connection, if we have 2 wires that cross, sometimes it's drawn with a dot in the middle. And then if you do not have an electrical connection when 2 wires cross, you will not see that dot. I've seen this drawn a little bit differently. If we don't have an electrical connection, there's typically a hoop, kind of like a freeway overpass. That's what I've seen as the most common, so I'll try to make that distinction clear. And then we will definitely see batteries. So the batteries, the most general type is having 1 positive lead and 1 shorter line for the negative lead. So this way is positive area of high potential to an area of low potential. Those are our 2 terms on a battery. You might see some of these other parts in a circuit, but we won't cover those in this lecture. So we have to follow a few rules when we're drawing the schematic symbols. So let's say we want to connect a battery and we want to put a light bulb in the circuit so that the electricity can flow through it. First thing on our list is that we need to draw the symbol for the battery and indicate the positive and negative terminals. So we know now that the positive terminal is the long side and the negative terminal is the short side. We also know that charges flow from the positive, the area of high potential, to the negative, which is the area of low potential. So looking at our second rule, we draw the wire or the connections from the positive to the circuit element and then draw its symbol. So electrons always, or not electrons, charges go from positive to the element, and then eventually we're going to go back to the negative terminal. So it's important to note that the flow of the current is going in this direction, even though we really know that electrons are flowing the opposite way, from negative to positive. But it's the convention that current or charge flow from positive to negative. So notice one other thing that I did here. I didn't draw a mess of wires as you might see in your house, but when we draw circuits, we draw them at right angles. So it's a little bit easier to draw these connections whenever we make a connection like that. So I'm going to skip down to the 4th bullet point and complete this circuit, because we know a circuit needs to be a circle. So we are going to complete this circuit through the resistor and back to the negative terminal. So that there is a complete circuit. Electrons would flow in this direction, so I will mark that with symbol I. This is the current. I misspoke. That's not electrons flowing through it, but that's charges. So going back to the 3rd point, if we have another resistor that we want to add in, and we want to make a different path, we can draw a connection symbol, so we can say that electrons, or the charges might have an option at this point. They might choose to go through this first resistor, or they might make a connection here and go through the second resistor. They have to choose one or the other. So when we do this, we draw a path to the second resistor. They go through this one and connect back to the original circuit. So we would have a connection point at both of these. Let's check our work to make sure that there are no dead ends, that electrons always have a place to flow through. Yes, they do. So they can take the first path through the first resistor or the second path through the second resistor, always flowing back to the negative terminal of the battery. We're going to connect ammeter in series and the voltmeters in parallel, which we will talk about once we define those terms. So looking at a series circuit, the definition of a series circuit is that there's only one path for current to flow. So in this picture down here, if you look at the picture on the left, we have a generator and then we have 3 light bulbs placed in the circuit somehow. We are assuming that these are going to be lit up, but you can see the mess of wires isn't really clear where the circuit is going. So the way that we would draw that is based on the picture on the right. So we have a generator here, or we might draw a battery for our class, and we're going to go this direction through the circuit. So remember, we're using right angles, and if you follow the path of the wires, all of the electrons have to go through all 3 resistors. There's no other choice for them to go. So we draw these as one element followed by another element. So anything where there is only one path for the current to follow, we call that in series. So there are a few rules for series circuits. Since the current has to go through all 3 of them, the current is the same for each element. There are no branches for the current to take, so it has to be the same. And then notice that we had 3 resistors, or 3 elements in there, so the effective resistance is the sum of all the resistors in the series. So we had one resistor, we had another resistor, and we had a third resistor. And so if we summed all of these up to take the total or equivalent resistance, you would say that the equivalent resistance is the resistance of number 1, I'll label these R1, plus the resistance of number 2, plus the resistance of number 3. I liken this to a traffic jam. If there's only one path for you to take to work and there are 3 accidents on that path, 1, 2, 3, you know that the equivalent resistance to your drive to work must be dependent on all 3 of these, and that overall you'll have a lot of resistance because you have to add up all 3 accidents. Also, the sum of the voltage drop is equal to the total voltage drop. So on your battery, you know you have some potential difference across this battery. Let's say we have a positive and negative terminal here, and this is a 12-volt battery. So from the positive side to the negative side, we have a potential difference of 12 volts. Well, when we go across each resistor, remember again that the definition of a resistor is anything, an element in a circuit that allows some voltage drop across the resistor. So if we drop some of the voltage across R1, some of the voltage across R2, and some of the voltage across R3, the sum of the voltage drop across all 3 of those is equal to the total voltage drop. Now, if we were connecting these in a circuit, like I'm doing now, we know that in order to go from the positive to negative terminal, we have to drop 12 volts. There's no other possibility. You cannot get back to the battery without having dropped those. So all of these 12 volts of potential will be dropped over R1, R2, and R3 total. The other type of circuit that we will look at is a parallel circuit. This is any general circuit where there are 2 or more paths for the current to follow. So we might see an example of a circuit that looks like this in the picture on the left, where we have a generator and then we have 3 lamps in the circuit. But if we want to connect them all where the electrons have a different path to flow, we can say that the current is going this direction. Let me draw a better arrow there. And then at this connection point, the first connection point right here, the electrons have a choice. They can either go this way or they can go this way. They cannot go both. And it's not like they get to choose which one they go. It's determined by the circuit in general. But think of the electrons as having one path to take, and they have to choose either one of those. So as the electrons flow, they will go down this way once they pass through R1. These electrons going through the first branch here have another choice. They can either go through R2 or they can continue on to go back to R3. And then it doesn't look like there's a connection here, but it is possible that we would have 3 resistors in parallel. So whenever you see a branch point in a circuit, you know that is a parallel circuit. So there are different rules for parallel circuits, and they're kind of flip-flopped with the series circuit. So in a series circuit, remember, we know that the voltage drop across all of them is the same. And in a parallel circuit, it's different. We know that the current is the same, or is the sum of the current through all 3 of the branches. So for example, in our last one, we had 3 resistors, and if we added up the current through resistor 1, through resistor 2, and resistor 3, that would give us the total current for the whole thing. This is saying that if we have a battery here, for example of a battery, we know that all of the current that leaves the battery has to come back here no matter what it goes through. So if it has 3 branches, the total current beforehand must equal the total current afterward, regardless of what happens in the system. One thing that's different is the equivalent resistance. The equivalent resistance decreases with more parallel resistors. So if I added in a resistor here, this is an example of a general series circuit. But if I'm giving the electrons more places to go, this is like saying if you're driving to your house and you know that there's an accident on one road, but you know a separate road to take, we have some resistance along this road and some resistance along this road, but half of the cars will go through one, half of the cars will go through the other. So the math on this is a little bit tricky, but make sure that you're just following the rules and you won't go wrong. So if we have R1, R2, and R3, the equivalent resistance decreases with more parallel resistors because there are more options for the charges to flow through. In this case, the voltage is the same for each path. So I like to do the finger test on this one. We know that if this is a 12-volt battery, and this is the positive and negative terminal, we start out with 12 volts. Oops, 12, let's say 12 volts, and when we get back, we should have a potential of 0 volts. Now, wherever the charges go, they have to drop all 12 of those volts. So if they leave the positive terminal and the electrons at the first branch choose to go through the first resistor, R1, we know that all 12 volts must be dropped over there because they will go through the resistor and flow back to the negative terminal. So that means R1, the voltage drop across it is 12 volts. Now if you follow the other paths, the electrons in the second path for R2 must do the same thing. R2, and then the same thing for R3. The voltage is the same in each path. One note about the equivalent resistance, to double check that, is that we are solving in this equation for 1 over the equivalent resistance. So when we do something called collapsing the circuit, which I'll show you in the next video, we are solving for 1 over equivalent resistance, so we will need to take the inverse of that to solve for the actual equivalent resistance of the circuit.